Diffusion is the passage of a gas through another substance. The substance could be a solid, liquid, or another gas. For example, helium diffuses through latex balloons. Care must be taken when providing examples of diffusion. Convection and mass transport, which is wind, also move and mix gases and do so faster than diffusion. Convection and mass transport will be faster in any uncontained environment, such as a home, classroom, or laboratory. Diffusion is the only transport mode possible in sealed environments. Effusion is the passage of a gas through a tiny hole into a vacuum. Systems that permit effusion can be created in a laboratory, but they do not occur in nature. Now we are going to calculate the relationship between the velocities and masses of two gases. So the RMS velocity is given by 3RT over m, all square rooted. Here we're going to just set, for two states, V1 over V2. And V1 over V2 will equal 3RT over M1 over 3RT over M2. Because these gases are at the same temperature, 3RT cancels. And this becomes equal to M2 over M1. Given that equation, we can now determine the relative rate of hydrogen chloride and ammonia diffusion. So to now apply that equation, we have V1 over V2 is equal to M2 over M1, all square rooted. For HCl, the molecular mass is 36.5 grams per mole. And for ammonia, the molecular mass is 15.0 grams per mole. So the labeling of 1 and 2 is relative. So if we just say that 1 is ammonia, we have VNH3 over VHCl. And that will be equal to the units cancel. And mathematically, this is 1.56. And so when we rearrange it, we find that the velocity of NH3 gas molecules is, on average, 1.56 times the velocity of HCl molecules. Now that we have that relationship, let's see what happens with the diffusion of hydrogen chloride and ammonia.
In this diffusion experiment, we're looking at the diffusion of HCl gas and ammonia gas. We have concentrated solutions of HCl and ammonia on the cotton in the tube. The HCl and the ammonia escape from the solution. The gas travels down the tube. The rate at which the gas travels down the tube is dependent upon the molar mass of the gases. When the gases come together, they react to form solid ammonium chloride, which forms a white solid in the tube. We see that the white solid is closer to the HCl side than the ammonia side. This is because the ammonia has a lower molar mass and diffuses faster than the HCl.
Diffusion also occurs with liquids and some solids. If you make tea by adding water to a tea bag and then forget about it, when you find it again, you will see from the color gradient that the tea has only diffused into the region surrounding the tea bag. If you do this in a clear glass, you can see the gradient from the side. When you add colored liquid to a plastic container and it stains the container, the coloring chemical is diffusing into the plastic, and quite often it doesn't easily come out. If you have traveled, you've probably seen this occur or even had this done to you. The wand picks up microscopic particulate matter from your bag, your laptop, your hands, wherever they swipe. The instrument is an ion mobility spectrometer, which is a special type of mass spectrometer. The ion mobility spectrometer works through a pseudo-diffusion process. So this is an ion mobility spectrometer. What we have in an ion mobility spectrometer is a chamber that looks like that. At the top is a detector. And at the bottom is our sample. And so this is the particulate matter that was collected from your luggage. In the ion mobility spectrometer, an inert gas is flowed through the chamber. And nitrogen is commonly used because it is inexpensive. Now, the sample is ionized with either electrons or X-ray radiation. This ionizing radiation ejects electrons from the sample, making them positively charged. The sample is now attracted to the detector, but it must pass through or diffuse through the inert gas. The larger the sample molecules, the more collisions it makes, and the longer it takes to reach the detector. Smaller molecules travel faster, positively charged. Bigger molecules travel slower, and very large molecules travel slower still. The detector measures the time it takes for the molecules to reach the detector. And if the time matches that of one of the drugs or explosives in its database, that is a positive test result. And it's generally bad news for the person whose luggage was just sampled.